This is AP Podcast 7.4, and we're going to talk about the effect of structure on acids and bases. So the first thing you need to know is that if we have any molecule with an H, it can be an acid potentially. And then how you can tell whether it's going to be a strong or a weak acid mostly depends on the strength of the bond and the polarity of the bond. So the stronger the bond between the hydrogen, the acidic hydrogen, and whatever it's attached to, the anion, the less acidic. So what you do is you look at the bond dissociation energies. How much energy does it take to break that bond? The greater the energy it takes, the weaker the bond or the weaker the acid is going to be, because it's going to take too much energy to release that hydrogen. The other thing you look at is the polarity of that bond. And then the higher the polarity, the stronger the acid is going to be. And for that, we're going to use electronegativities. So this first table that we're looking at compares the bond strengths of some different halogens and their hydrogen. So bond strengths and acid strengths for hydrogen halides, and halides is another word for halogens. Electronegativity decreases as you go down the periodic table, but what we see when we look at these, we know that hydrochloric, hydrobromic, and hydroiodic acid are all strong acids, but hydrofluoric acid is a weak acid. And the reason it's a weak acid is because that fluorine has an unusually strong hold on its hydrogen. It doesn't want to let it go. And in order for it to be a strong acid, that bond has to be broken and the hydrogen has to be let go. So the chlorine, the bromine, and the iodine, you can break those bonds and they can be released. But this hydrofluoric acid, that is a weak acid because the bond strength is too high and it doesn't want to let that hydrogen go. The other thing we look at is the polarity of the bond, and in this case what we're going to focus on is called oxyacids. They're acids with an oxygen and the hydrogen. The more polar that bond is, the stronger the acid's going to be, and we just talked about that. And how you can create these polar bonds, more polar bonds, is when we get more oxygens hooked to the central atom. So the more oxygens you get, the more acidic the hydrogen becomes and the stronger the acid is. So here's an example. Here's perchloric acid, which we know is a strong acid, and if we wanted to look at a Ka value of it, which they hardly ever give you, we know it's really large. It's around 10 times 10 to the 7th. So a very, very strong acid. As we go, though, and we decrease the number of oxygens by 1, so we go from perchloric to chloric acid, and then work our way down, we can see that the Ka value drops. So here's the strong acid, but beyond that, they become weaker and weaker and weaker, and the Ka value drops down. That's because there's fewer oxygens, and the bond is not as polar as it is up here. And I have some diagrams of this that'll kind of help explain it. We have sulfuric acid here, which has a large Ka. We know the first proton on sulfuric acid is a strong acid. And then we have sulfurous acid, and we can see that the Ka drops significantly. So anytime you lose the number of O's, the Ka value drops and the acid becomes weaker. So oxyacids, just like we were saying from that table, the more oxygens you have, the more acidic it is. And when you're thinking of these, remember that the H is not attached to the chlorine, because that's how it appears from the way that you write the formula, but the hydrogen is actually attached to the oxygens, not to the chlorine. And we know oxygens are electronegative. They like to hog the electrons. So when they're hogging those electrons, they're pulling electrons away from the hydrogen, and it creates that polarized bond that we talked about, and that's when we get those stronger acids. So in this diagram that you're going to see, we have electron density. And electron density is, this is the way the electrons are going to go. They're going to get pulled away from the hydrogen towards the oxygen and the chlorine. So the electrons are going to go this way. As we go through these and we start adding O's, though, what you see is the electron density gets bigger and bigger. So here we are at perchloric acid, that strong acid. And when we've tacked on these 3 O's on the end, you can really imagine how all these electrons are just getting pulled in this direction, and hydrogen is going to be left with hardly anything. It's going to become a very polarized bond, and that hydrogen is just going to break right off. So if we flip back through them, you can see as we add those electrons, the electron density gets bigger and bigger, and it starts polarizing that bond. The last thing we're going to talk about are acid-base properties of oxides. And there are two types of oxides. There's non-metal oxides and there's metal oxides. So non-metal oxides, here they have the sulfur trioxide. If you have a covalent compound, two nonmetals, they're going to create an acidic solution. What's going to happen is, for our example here, if we take sulfur trioxide and we put it in water, and this is gas, so maybe we're bubbling this gas through it, we're going to end up with sulfuric acid. And we know sulfuric acid is a strong acid, so it ionizes, and this is actually what happens. The sulfur trioxide bubbles through the water and it forms hydrogen ions and this bisulfate right here. So anytime you have non-metal oxide, any sort of covalent compound, you're going to form an acidic solution. So the opposite then is if we have a metal oxide, and a metal oxide will form a basic solution. When metal oxides, which are ionic, are going to dissolve in water, they're going to produce bases. The example we have here is calcium oxide, calcium being the metal. If this is put into water, we end up with calcium hydroxide. And calcium hydroxide is going to ionize to an extent and form hydroxide ions. So metal oxides form a base. Non-metal oxides are going to form acids. And this is something that they would expect you to know and you need to know. So remembering what will form what when we put things into solution, and then also understanding how those how the strengths of acids work. How are they related to electronegativities and to polarity and bond strength, and you can explain all of those things. So that's it. It was a really quick thing. Just understanding the structure of what you have will help you explain why things are strong or weak. Then also it will help you describe what happens when you put certain compounds into a solution. Is it going to form an acidic solution or a basic solution?